Previously, we talked about what a regular language is. So remember, a regular language, at least one definition of a regular language, is that there exists a DFA, a deterministic finite automaton, for which it recognizes this language. So if you have a DFA that recognizes the language, we can call it regular. So you might ask, Dad, what the heck is a regular language? So one way I like to introduce this topic is to bring up the idea of regular operators, which have a bearing, they bear the same name, right? Regular. So we're going to talk about regular operators. So this is just to take a little break from designing DFAs. So you can define so-called regular operators, and we've actually seen some of these already, actually. So I'm just going to be now talking about them in a broader sense, talking about languages. So you can define these operators on languages. So it doesn't have to be that it has to be specifically a regular language. You can use these operators on just languages. However, there's special properties that these operators have on regular languages. So given two languages, languages A and B, below are examples of regular operators. So for our example here, I'm going to have two languages. I had to pick some fun ones for us. So A is going to be equal to the set that contains the string dog and cat. And B is going to be muffin. So it's going to have the string muffin and the string cake. So I'm going to presume that these languages are defined over using say, ASCII characters, for example. Or it could even be lowercase alphabetical letters. So here's some examples of regular operators. So the first one that usually talk about is union. So one way to write out union is using the cup. So you use this cup notation. So if you've seen set theory before, you're gonna know what you're in for right away. So the result of performing a union operation is that it'll contain every string x such that x is in A or x is in B. So notice the or there. So this is just a typical union operation. This is actually how you might go about just defining what union is. So in plain language, you're just going to lump the strings together without multiplicity, of course. You don't write out the duplicates. This isn't a multi-set. So I'll say into one set from A and B. So just as an example, let's use A and B as I define them up here. So it would have dog, cat, muffin, and cake. So notice how it just lumps all the strings together, and you don't include the duplicates, right? You wouldn't write, even if that language B had cat also in it, you wouldn't write cat twice. You would just have cat once, right? It's a set. Sets don't include duplicates. So anyways, that's what union's all about. Piece of cake, right? If you've heard of a set before, you probably have heard of union before. It's the same definition. So next, I got to talk about concatenation. We previously talked about concatenation, but I haven't talked about concatenating languages. So some would write this as A dot B, or even make this a solid dot. But often it's just written. So it could be the hollow dot. It could be a solid little dot like multiplication. Often it's just written as AB, just A and B right beside each other, whenever clear. Is as follows. So AB, so A concatenated with B, that's how I'd read this, is you're going to have XY, so it's just a concatenation of two strings, such that A is in A, sorry, X is in A, and Y is in B. In plain language, all this is saying is take every string in A and concatenate it. Concatenate each with every string in B. So just as an example, if I have A and B, as with dog, cat, B with muffin, cake, AB, the concatenation of A and B, would be dog muffin. So I'm just going to do dog muffin first. Then I'll do dog cake. So I'm just going to take this one, concatenated with muffin. Then I'll concatenate dog with cake. And then I'll concatenate cat with muffin and cat with cake. With cake. Let's say cake. No, it's cake. You know, the stuff you eat. And then I have dog cake. And I got cat muffin, right? And cat cake. So far we're doing pretty okay, right? So we got union, concatenation. Another operator that we actually ran into previously was star. Or some would call this Kleene closure. Or Kleene star. So another operator is star. So sometimes it's just called closure. I'm getting really excited here. So sometimes it's just called closure as well. Or it's called Kleene closure or star. Just as a remark, much of this discussion about regular languages, a lot of the theory was developed by the logician Stephen Cole Kleene. So if you're wondering where it gets its name from, that's who it's given that name by. So it's named after this logician. So we know the star operator, but you'll notice that I'm going to have to define it now for any language. So it's something you apply to a language. So I have the language. It's almost like you raise it to an exponent. We talked actually about this before. But now I'm going to use star on any language at this stage. Previously we talked about with an alphabet. So I have x1, x2, x3, up to xk, such that k is greater or equal to 0, and each xi is in the language A. Notice I'm talking about a language here, not an alphabet. So now, you might ask, what the heck does this mean? So adopting the power notation, but applying it it strings instead of symbols, so just like a symbol like we did before, with our example, what I'm actually writing out when I say something like this is actually all. Let me just write it out. You'll see what I'm talking about. So a star, akin to what we talked about before, is a to the power of 0. Now, this is all of the strings whose length is going to be so when specifically we're talking about how many of these you pick out, right? Remember last time when we used the star when it came to the alphabet, it was all strings that were what? All the ones of length 0, then all the ones of length 1, all the ones of length 2, all the ones of length 3, and so on. But now notice that now when I write x1, x2, x3, all the way up to xk, now we're picking out strings from the language, right? So this is saying, so now instead of thinking about it as strings of length, now we're taking how many of the strings from the language. So notice I'm taking none. So what would that correspond to? Well, this is the same as me writing out a language for which it only contains the empty string, because I didn't pick any strings, right? Union A1. Well, here it says to pick one of our strings. So I have dog, cat. So I could pick one, or I could pick. So I could pick dog or cat, right? Right. It's all of the strings that. So if I pick out one of them, so if I pick out none of them, I get just. I have none. I have none. But they're in. But please take note. This isn't the empty language. Please take note of that. So take our A, and we'll raise it to the power of 2. That means I'm going to pick out 2 strings. But notice that what I do to them, I concatenate them. So now this would just be where I have x1, x2, where each one is some string in this language, right? So what does that mean? Well, it's going to be dog, dog. So I'm going to concatenate dog with itself twice. And then I can have dog, cat, right? Right? Those are 2 possible ways. But I can also write cat, cat, right? And I can also write cat, dog. So it's 4 possible ways to take our strings and pick 2 of them and concatenate them like this. That's all it says. So that's what A squared, I guess, would be. And you'd keep repeating this process, akin to what we seen when we did use the star operator on an alphabet. Same idea, just instead now we're picking out strings from the language and concatenating them with each other. In this case, namely, like I said, you aren't picking any strings, so the only strings of length 0 that we have is the empty string, right? That's the only one that exists. So it says, okay, well, the string is of length 0, but yeah. This actually makes this notation actually helpful when I talked previously about an alphabet with the plus. This would omit, for example, this one right here. So now let's talk about why we call regular languages what they are, okay? It's because of these so-called regular operators. So there's languages that have a very nice property as follows. So we talk about what these regular operators are. Where the regular languages get their name from has a lot to do with these regular operators. So all regular languages are closed under regular operators. So when remember I can use regular operators on any languages, right? But suppose I give you two regular languages. Suppose if L1 and L2 are regular, so if I give you two regular languages, and remember, one way you can define a regular language is that there exists a DFA that recognizes said language, right? So what it says is that if I take L1 union L2, that is regular. So this is actually regular too. So if I take the language L1, take the language L2, and I perform a union operation, it's still regular. Likewise, if I concatenate L1 and L2, this is also regular. Likewise, L1 star is also regular. So this is also regular. So this is something nice that the regular languages have. They all are closed under these three operations. So this is just something that regular languages have as a property. So you might ask, okay, so how exactly do you go about proving this? So just to be very clear, just again, what closed means. It means that if I give you two regular languages and I perform the union operation, the question is, since these are both regular languages, does it remain regular? So is it closed under this operation? So how exactly to prove this, we could present DFAs, right? Because that's what the definition I gave you was, right? Because it has to be a DFA for this language, to recognize this language, there has to be a DFA for this one as well, right? So one way you can go about this is you could try presenting DFAs that show the result of performing this operation there is a DFA. But I would argue it's a little tricky, okay? In fact, it may be much easier to go about it with something else. So however, we will see, so this is something we'll talk about eventually. We will see by adopting a different but perhaps I'll use quotation marks around general because it isn't actually true that it is more general, but it describes things in a very general looking kind of way. So, however, we will see by adopting a different but perhaps general-looking model how to prove these claims easier. And if you wonder what I'm talking about, you may or may not have heard of what we call regular expressions. That's what I'm referring to. So this different but general looking thing, this is what I'm referring to as a regular expressions. Again, same usage of regular. So using regular expressions, I'm saying that it's actually easier to prove these claims. In fact, there's a very close relationship to all the concepts we're talking about with regular expressions.